Okay, welcome back to Investigation 1. So now we're going to do a few more limit statements. I'll use the three different methods again. And for problem 3, we're trying to make a general conclusion about exponential type functions where the base is either greater than 1 or between 0 and 1. Okay, so for problem 3a, for exponential functions, g of x equals a to the x, where a is greater than 1, we're going to complete the following limit statements. So you may use a table or you may use a graph, okay? You can kind of like eventually just say that you did it algebraically as well, like we just want to know what the answer is for these. So for the first one, I guess like we can do a table. And then for the second one, we can do a graph. And then for the third one, we'll do it algebraically, just so that you guys are clear on what the three methods are. So we're talking about a function such as like e to the x, 2 to the x, 5 to the x, stuff like that. And we want to know in part 1 what happens as x approaches infinity. And in part 2, what happens as x approaches negative infinity. So let's make a table, okay? First of all, let's make a little table. So let's make a table for, say, 2 to the x. And if I want to know what happens as x approaches infinity, I should use pretty big values of x. Like I'll use 10, 100, and 1,000 and see what happens there. So I will be plugging 2 to the 10 is 1024. And then 2 to the 100 is already like a huge number that my calculator can't even plug out. 2 to the 1,000, I'm getting like the overflow, but we know that 2 to the 1,000 power is quite a large number. So it seems like as x gets bigger and bigger, y gets bigger and bigger. So we can say that as x goes to infinity, y goes to infinity. These are bigger and bigger numbers. And it didn't really matter if I used 2 to the x, 5 to the x, e to the x. Those are all going to produce large kinds of values. Okay? And then for the second part, we want to know what happens as x goes to negative infinity. So that means that x will be like a huge number, like a million or whatever, but it's going to be negative. So for this one, we can make a different table. We could try, say, 5 to the x, just to have a different example. And then I'm going to use negative of big numbers like this to get started and see if I can find any kind of a pattern. Okay, so I take 5 to the power of negative 10 on my calculator, and I get already 1.024 e to the minus 7. So really, if you think about it, this is 1 over 5 to the 10. Like my calculator can't even handle such a small number. Okay, so this is 1 over 5 to the 100, 1 over 5 to the 1,000. And then what kind of numbers are these? These are very small numbers close to 0. Okay, so in other words, 1 over a big number, as we said earlier, is a small number. And so it seems like the limit as x approaches infinity of g of x is 0, okay? It's 0. We could check this graphically just to ensure, like, you know, we know that a is here, whatever a is, we know that it's bigger than 1, and the graph of the exponential function a to the x looks like this. So it kind of makes sense, like, as x goes to infinity, y goes to infinity, right? But then on the other hand, here, as x goes to negative infinity, y goes to 0. So both the table and the graph support us, okay? And then in part B, let's see if it makes a difference if a is a number between 0 and 1, such as, for example, 1/2 or 1/5 or 1 over e or something like that. And in part B, it asks us to plot some exponential functions to consider the limit statements. So maybe let me plot a couple in Desmos just for fun. So we're talking about, so for example, let me plot it for, say, a equals 1/2 a equals 1/5, and a equals 1 over e. And we're going to be plotting a to the x, okay? So let's look at them. So if a equals 1/2, then I would have 1/2 to the x power. Look at that graph, okay? I can also plot 1/5 to the x power. It almost looks similar. They're on top of each other. The purple one covered the green one. If I zoom like way in, we can start to see that they're technically different. But remember, I don't want to zoom way in. I care about what happens as x goes to infinity, so I'm going to keep it zoomed out. And then I'm also going to do 1 over e to the x, and that's in black. It also looks similar. So, okay, that's cool. That lets me know that probably what the graph will look like is something like this, right? That's what all those graphs were looking like on there. So this is when a is between 0 and 1, and then we have the opposite. So in this case, as x approaches infinity, y is getting smaller and smaller and approaching 0, but as x is approaching negative infinity, y is getting bigger and bigger and approaching infinity. So we see that with exponential, it depends on the base, okay? And this also makes sense if you think about it just in terms of like plugging something in, because if I have, say, like 1/2, and I'm going to take it to the 100th power, like, so this would be kind of corresponding to this. This is the same as 1 over 2 to the 100th power. So this is 1 over a big, which is a small, right? And then similarly, if I had 1/2 to the negative 100th power, then this is the same as 2 to the 100th power. So this is a big. So it kind of makes sense if you think about it in a different way too. So we have basic information about limits of exponential functions. It's good if you remember these results, you can cite them later without having to do the computations again. But if you forgot, it's also okay to do the computations again. Okay, and then I just wanted to show you one more example here in part C, a little bit more algebraic one. Just some of the tricks of the trade, basically. You could also make a table and look at the graph for this one. There wouldn't be anything wrong with that, but you'll see stuff like this in the online homework. So, okay. So when you see like a limit, this is the limit as x approaches 0 of the square root of 6x plus 1 minus 1 all over x. So the first thing you can try is plugging in x equals 0. You can try. If I plug in x equals 0, what's going to happen? I would get the square root of 0 plus 1 minus 1 over 0. Already, it's undefined because 0 is in the denominator, and even worse, if you simplify, we get 0 over 0. Okay, so this is absolutely undefined. Okay, when it's like that, that means that you need to simplify first and then plug again. How do we simplify this? Well, if it's a rational function, like problem 1, we could try factoring, but because this function has a square root in it, I'm going to try a little trick, which is using the conjugate. Okay, all we basically ever do is either add 0 or multiply by 1, and in this case we're going to multiply by 1 in a special form, which is the square root of 6x plus 1 over itself. Okay, I use the conjugate of the numerator to try to simplify. So now keep in mind the fact that there's parentheses here and here. I'm not going to worry about the denominator, so I have to FOIL or properly distribute everything. So I'm going to keep the limit there and not do anything with it until after I've simplified. So when I simplify, I'm going to have 6x plus 1, which is the square root of 6x plus 1 times itself, Okay, that's the first term, and then I have to subtract the square root of 6x plus 1, and I need to add the square root of 6x plus 1, and I need to subtract 1 on top. On the bottom, actually, let me just keep it because I just want to see if the top part will simplify. Okay, you could distribute the x if you want, it wouldn't be wrong. But what you're going to notice is we have a nice cancellation on the numerator. So I can say that this is the limit as x approaches 0 of, and actually there's another cancellation on the numerator. So we have 6x plus 1 minus 1 now. And I keep the denominator the same. Okay guys, don't go too crazy with cancellations. I don't want to see any illegal cancellations, but plus 1 minus 1 is definitely safe. That's 0. So now we have the limit as x approaches 0 of 6x over x times root 6x plus 1 plus 1. Okay, and then now we have another cancellation because x divided by x is equal to 1. So I can safely cancel that. There's no addition, which would cause this to be illegal. And this is a good cancellation because the x equals 0 on the denominator was part of what was causing my problem. So now I have the limit as x approaches 0 of 6 over the square root of 6x plus 1 plus 1. So now that I've simplified it, I can try plug again. Okay, so now I plug in x equals 0 for x. I don't know for sure if it's going to work out or not. If it doesn't work out, I'm just going to have to try something different. That's part of calculus, I guess, is like becoming comfortable with different, you know, you might have to like redo something over and over and over, but in this case, it's going to work out. So I would have 6 over the square root of 0 plus 1 plus 1. So that's 6 over 2. And 6 over 2 is equal to 3. Yay, it worked. So totally we can say that the limit is equal to 3. So that's the end of the first investigation on limits.